A recent and remarkable discovery by a NASA space telescope has sparked a wave of excitement across the astronomical community, particularly among the team of scientists who have devoted themselves to studying Comet 3 I/Atlas. This excitement stems from observations made by the Neil Gehrels Swift Observatory, a space-based telescope that managed to detect a faint ultraviolet signature coming from the comet, an achievement that ground-based observatories simply could not match due to Earth's atmosphere blocking much of that light. The finding has been described as a major breakthrough in understanding how comets evolve, especially because of the highly unusual circumstances under which the comet was observed. It is not simply the scientific feat that has captured the attention of researchers, but also the enormous implications this discovery holds for understanding planetary formation across the Milky Way and the potential habitability of planetary systems far beyond our own. Comet 3 I/Atlas itself has been an object of immense curiosity since the moment it was spotted on July 1, 2025. Unlike typical comets that orbit the Sun in predictable, elongated paths, 3 I/Atlas is an interstellar visitor, meaning it originated outside our solar system entirely. This makes it only the third known interstellar comet ever detected, following 2 I/Borisov in 2019 and 1 I/Oumuamua in 2017. Its presence is temporary and fleeting. It entered our solar system from the depths of interstellar space, will swing past the Sun, and eventually depart again, never to return. Because its time within our observational reach is so limited, astronomers have been racing to collect as much data as possible before it disappears back into the void. What makes this comet even more extraordinary is its estimated age. Early analyses suggest that 3 I/Atlas may be around 7 billion years old, significantly older than Earth itself, which formed roughly 4.5 billion years ago. This would make it the oldest comet ever observed by humanity. Rather than being a member of our local cosmic neighborhood, it is a primordial relic from another star system, likely formed when its home star was still young and surrounded by a protoplanetary disk of dust, ice, and gas. Over billions of years, the comet must have been ejected from that system, possibly through gravitational interactions with young giant planets, and sent drifting alone through the interstellar medium. To observe such an object is to peer directly into the early chemical history of another star system, preserved in ice for eons and only now warmed by our Sun for the first time. Because of the comet's unusual trajectory around the Sun, there have been long stretches of time during which it was hidden from Earth-based telescopes. To fill in those observational gaps, scientists even coordinated Mars rovers and Mars-orbiting spacecraft to track 3 I/Atlas during periods when its position relative to the Sun made it impossible for Earth-based observatories to see it. This interplanetary collaboration underscores just how important and rare this object is, and how determined astronomers are to gather as much information as possible before it vanishes forever. The key scientific milestone in this new discovery came from the Swift Observatory's ability to detect hydroxyl, OH, gas around the comet. Hydroxyl is produced when ultraviolet sunlight breaks apart water molecules, meaning its presence is a direct indicator that water ice is sublimating, turning from solid to gas, as the comet heats up near the Sun. 4 comets within our solar system. Detecting hydroxyl is a standard and reliable way for scientists to measure their activity levels. The more water that is being released, the more active the comet is considered to be. However, seeing the same chemical signature in an interstellar comet is groundbreaking because it confirms that some of the same processes that shape our local comets also affect comets formed around distant stars. The ability to measure water-related activity in 3 I/Atlas gives astronomers a new tool for studying interstellar visitors. Instead of relying solely on imaging and trajectory analysis, they can now compare the chemical behavior of 3 I/Atlas directly to the well-studied behavior of comets that originate in the Kuiper Belt or Oort cloud. This comparison allows researchers to ask important questions. Are comets from other star systems chemically similar to our own? Do they contain the same kinds of icy mixtures? Do they release gases at the same rates when heated? Each answer helps narrow down our understanding of how typical or atypical our own solar system might be compared to planetary systems across the galaxy. The detection of hydroxyl in particular is important because water is one of the most essential ingredients for life as we understand it. It does not guarantee life on or around the comet, of course, but the presence of water ice in an object formed around another star offers an important clue about the prevalence of water throughout the galaxy. If interstellar comets commonly carry water, then water-rich material may be far more universal than previously assumed. Such material could be scattered throughout the galaxy by young star systems and later delivered to planets during periods of heavy bombardment, much like many researchers believe happened on early Earth. Water-bearing comets, therefore, may be a galactic mechanism for spreading the key components of habitability. The significance of the Swift Observatory's ultraviolet detection lies not only in what it reveals, but also in how it was obtained. Ultraviolet wavelengths never reach the ground because they are absorbed by Earth's atmosphere. This means that only space-based observatories, like Swift, can detect the faint ultraviolet glow produced by hydroxyl molecules. In the case of 3I/Atlas, this glow was extremely faint, so faint that even the best ground-based instruments had no chance of observing it. Without Swift's unique capabilities, scientists would have missed this chemical fingerprint entirely. The discovery also adds to the broader scientific importance of interstellar objects. Each one that has been observed so far has revealed something surprising and previously unknown. Oumuamua, the first interstellar object ever detected, baffled astronomers with its unusual shape, acceleration profile, and lack of a detectable coma. 2I/Borisov, in contrast, appeared much more like a typical comet, complete with a glowing tail and water-driven activity. Now 3I/Atlas seems to be offering another piece of the puzzle, confirmation that interstellar comets can indeed carry water ice that behaves just like the ice in comets that formed near our Sun. With each new interstellar visitor, scientists gain a clearer picture of what kinds of objects populate the galaxy and how they relate to the building blocks of planetary systems. At the same time, 3I/Atlas presents scientists with a rare opportunity to observe how such an ancient object reacts to the heat of our Sun. Having spent billions of years in the cold vacuum of space, the comet's ice and dust are likely pristine and unaltered. When it enters the inner solar system, that ancient material begins to warm and release trapped gases. By analyzing the ultraviolet emissions produced during this process, astronomers can reconstruct the comet's composition and investigate whether the chemical environment of its long-lost star system resembled our own. These insights could reshape our understanding of how planets and comets form under different stellar conditions, and how the availability of water and organic molecules might vary from system to system. The fact that 3I/Atlas is thought to be older than the Sun means it formed at a time when the Milky Way itself was younger and chemically less enriched. Over billions of years, star formation has gradually increased the abundance of heavy elements like carbon, oxygen, and nitrogen, elements essential for forming complex molecules. Studying a comet that predates much of this enrichment could reveal what early planetary systems were made of, what kinds of materials were available, and whether such ancient environments were capable of supporting the precursors to life. It is extremely rare to have access to a sample of material that has survived intact from that era, and interstellar comets like 3I/Atlas are one of the only possible sources of such information. Scientists are also interested in how the comet arrived here. Interstellar comets are typically ejected from their home systems through gravitational encounters with massive planets. These encounters can fling the comets into interstellar space, where they drift for billions of years before possibly passing through another star system by chance. By reconstructing the orbit of 3I/Atlas, astronomers can learn about the trajectory it followed through the galaxy and potentially identify the kinds of stellar environments it may have passed near. Although it is nearly impossible to determine its exact origin, modeling its motion gives scientists a window into the dynamic processes that shape planetary systems and scatter icy objects across the galaxy.